Szczerbinski. I'm with Packard, and actually the first speaker is starting off here. Our host, Steve Goodwin from Marquette University, is not in the room at the moment, so on behalf of him, he welcomes you. He will be here at the end to thank you for coming. So this is kind of an educational little series that we're doing here to talk about some new things that are happening in the networking world, specifically in the area of software-defined networking. So what I'm going to do is I'm going to take you guys through what that means, kind of the history of it, and where things are going to go with it. And then after I've done, what we're going to do is we're going to have a demonstration specialist, David Spears from HP, who's actually going to demo some of our production software and hardware that runs SDN today. And then lastly, we're going to kind of like look towards the future, and we've asked Aaron Stewart from the University of Wisconsin, who's a grad student there, but coincidentally enough, used to be an undergrad here, and he is going to talk about some of the SDN research that he is doing right now over at UW. So that will be our lineup, and then afterwards we'll have time for questions and things like that. So where does SDN end up? Why are we here? Why are we here talking about SDN? And it's really because there's a bunch of trends that are going on right now within IT. And a lot of these trends in IT today are being pushed because IT is being stretched so far, right? There's so many new applications that are starting to come out that ask for a lot of information, and ask for a lot of information anytime and anywhere. And that's to deliver those applications, it means that the IT infrastructure that we put together has got to become a lot more scalable and a lot more flexible. And so we see a lot of trends that are going on there right now. And some of those trends have been going on for several years. Like this first trend that's on the left here, which is converged infrastructure. How do we simplify up how servers, storage, and network talk to each other, right? And in a lot of cases, how do they physically connect to each other in a lot more efficient way, and how can we manage them better in a lot more efficient way? Then, how do we provide tool sets so we can actually take that data center and make it a little bit more massive? And these are tool sets around the whole area of the software-defined data center, being able to either ask the data center to expand and shrink based upon what's going on, or even have the data center react automatically, right? Bringing up server instances and taking them down automatically based upon loads. And that's within my own data center, right? So there's also this trend of where I might not have the capability for all the compute and storage in my own data center, and I might need to go use other data centers to get that compute, that storage, right? And that's where the cloud comes in some cases. And how do I migrate workloads from my data center out to the cloud and potentially back again? But obviously a lot of that stuff underpins the network, right? And it underpins how do we automate how people get to those applications, how do they get to the storage, right? And if we have applications that migrate from one data center to another data center, or they're on one machine and now they're on 100 machines, we need the network to be a lot more flexible. And that's what we think is really, really important, because as we've been doing this the last 2 years, being able to pull it off has become massively complex, right? So if we utilize, and it's kind of interesting, the tool sets that we've utilized to do it are the same tool sets that we've had for ages. I mean, I'm a career networking person. I got my start at UW here in Milwaukee back when there was no DNS, right? And a lot of the tool sets that we have today, it's kind of funny, they're all based on these really old tool sets. So let me give you a good example. Virtual LANs. They've been around since the 90s. And you can only have 4,000 VLANs based on the old VLAN structure, right? With only 4,000 VLANs, it means if I go to a data center and I want to carve up that data center so certain apps can talk to certain other apps, I get pretty limited by 4,000 of them, right? Especially if I'm in a very large data center. Or other protocols like spanning tree that limit what path things can go on the network also limits me. But one of the areas where I get really limited is in the fact that As my network expands, whether it be in the data center or in the campus network, it means that if I have to roll out network policy, it means that I'm typing commands in a switch or a router or some network device, right? And so say I decide that I want to change how a group of people access one application, or maybe I want to not allow them to access an application. It might mean that I need to put filters for access control lists in the network, right? I need to do it consistently all across the network to block people from getting places. If I have a lot of devices, it means that I have to execute the same commands over and over and over in lots of devices, right? And every time for every different application, if I have to make a change to the network, that change adds up dramatically, right? Now, there's been tool sets over the years, network management tool sets, or network orchestration tool sets that help to automate this, but when it all comes down to it, I'm still entering commands inside of network devices, right? And it means that the speed of change can be really slow, even if I automate it, right? And it also means that the rate of change of a mistake can potentially be really broad and really fast if I've automated it too, right? So that has become one of the challenges in building out large-scale networks, is getting network policy correct in all the different places all the time. It takes a lot of effort to do it and do it right. Now, I always like using analogies in terms of how we look at things. So if you imagine, the roadways themselves, right? So here's the challenge. We get on the road, and we want to go drive down to Marquette here to watch this talk. I got lots of different choices, right? I can choose which route I go, which road I go on. I might change the route based upon hitting a stoplight, traffic exit my way, things like that. But for me coming to Marquette, it's really not a big deal. I mean, honestly, if I take the wrong route, or I get stopped in traffic, or I hit a stoplight, I might arrive 5 minutes later, 10 minutes late to the talk. It's not the end of the world. But if I'm a fire truck, or I'm a police officer, and I am trying to get to an incident as quickly as possible, running into traffic and taking the wrong route and hitting stoplights is the worst thing possible, right? It's going to cost me time, and someone's life might be on the line. And in the world of, the roadways, there really isn't a really good automated way for that stuff to all happen. But, if you can imagine that if we automated the roadways, if we had the ability to say, hey, there's a fire truck going to a fire, wouldn't it be great if I could actually, along the way, know where the fire truck is at, tell the stoplight that's in front of it to turn green for me and red for everybody else, right? So that I could actually give the best path possible to the fire truck so that they can get to the fire on time and save people's lives, right? And that's that kind of that analogy the way networks work today, but the problem is that networks don't necessarily work that way. We don't necessarily say, oh, there's really important traffic, let's put green lights on all that traffic, right? Because networks don't work that way. They work a lot like the roadways do today. I go down a path until I get to a network device, and that network device decides what to do with me, and then I get sent on another network path. There isn't an end-to-end path that gets programmed for me. It's just like the roadways today, right? My path keeps getting looked at every single stop of the way. So what we really feel, and I think what the industry really feels, is that we need to stop focusing less on infrastructure and actually start focusing in on, delivering the applications that we want to deliver, right? And that's kind of the problem we have today. Is we're so stuck. And honestly, if I think about it, over the last 25 years, network devices actually haven't changed much at all, right? Now, they've gotten bigger and they've gotten faster, but they haven't changed at all. Network devices still all make their own decisions, and I still program individually all my network devices, which really seems kind of strange, right? Because if I look at applications, if I look at servers, I look at storage, there's a lot of automatic provisioning that goes on. So, sorry about that. So, new way of going out there and programming networks. And programming networks that can meet business objectives a lot better, that have the flexibility in how you actually utilize the network, and maybe utilize it differently for different people at different times. The ability to actually rapidly deliver applications across it and change up that network of those applications. And if I can do it in a way that's easier to program, it's actually going to lower operating costs, lower expenses. So here's where software-defined networking comes in. So at the bottom of the software-defined network, we still have to have infrastructure items. We still have to have physical Ethernet switches, Ethernet routers, firewalls, right? Because things still have to connect to the physical world. And I even consider wireless part of the physical world, right? Because I have to talk to a radio that's actually going to get me out to a device, right? So I still physically have to have something. I can't replace a radio with software. I can't replace an Ethernet wire with software. So I still need those things. But on top of it, though, I can, if I want to, control them in different ways. So I need to have a control layer that allows me to actually control those devices and control them en masse. But then as well, I want an easy way for the outside world to talk to that control mechanism and be able to tell us things, right? And maybe not just from my IT perspective, but maybe potentially as well from other applications perspective, right? Who's to say that the building might not want to tell the network about something? Or maybe the network wants to tell the building about something. Or maybe a patient in a hospital, maybe we're wondering where that patient is in the hospital, and maybe the network can actually tell us where that patient is in the hospital, right? So the applications we're talking about go past the network, right? In a software-defined network, we want those applications to be able to get that data from the network to be able to tell those applications about things. So in a software-defined networking world, like I mentioned before, at the bottom layer we still have to have network devices, right? And instead of those networking devices making their own decisions, we actually now have a way that we actually tell them what to do, right? So there has to be an open programmable interface to be able to tell those network devices what to do, right? And they get their instructions through something called a controller, right? And we're just going to use a block diagram here to define a controller. But that controller can tell all those devices in a very efficient manner exactly how to move traffic through the network, right? Then another API that can allow applications to tell the controller things that they want, or the controller to tell them things itself. So this whole idea of software-defined networking is actually not all that new. It's actually been going on for several years here. It all started off with some experimentation that was done at Stanford University. The project name is called FAME. This is back about 2007-ish. And they got this great idea of actually, taking a network device and splitting it apart like I've talked about into these three different pieces. And when they first started doing it, they were doing it all in software. Essentially what they did was they took a switch and they wrote a software version of the switch. And then they created devices and software that would connect to that switch and essentially emulate hosts. And then they wrote a controller application that could tell that switch and other software switches on what to do. And they got to a point where it seemed like the concept kind of worked. They split apart essentially the control plane from the data plane of a network device. And then they started to say, hey, this really works in software. I guess we need to try it in the real world. So if you know your geography and also your history, you know that Stanford University is just a few blocks down from the headquarters of Hewlett-Packard. And of course, if you also know your history too, that Bill Hewitt and Dave Packard went to school at Stanford and actually became some of the biggest donors to Stanford over time. So there's this rich heritage to it too. But they said, hey, we need some hardware so we can try this out. So we said, okay, we think we can do that. Give us the specs, we'll write it out. We wrote some test code. We came on over with one of our HP Pro Curve switches, got the test code on it, they started to play with it, it worked. And so there's been years of work with them, and as well as since there was an open community, there was a lot of other folks that worked with them on this as well. Out of that, what I think is the most interesting is the fact that at a certain point they said, hey, this could become the standard. I guess we should probably go to the IEEE or the IETF and let's put together a draft standard for this and submit it. And there was actually some thought that maybe that wasn't going to make any sense. And so they said, you know what, if we put it in the IETF or we put it in the IEEE, you know what's just going to happen? The darn manufacturers out there, the HPs, the Ciscos, the Junipers, all they're going to do is sit and argue about it, and they're going to stretch out the time that it takes to get the standard out there, right? So we don't like the idea of both those organizations being very vendor-driven, right? So we wanted to actually release it in a different way. They said, why don't we form our own organization, and let's have end users be the people that decide on the standard. And let's have the vendors be the people that can be involved, but they can't really vote as much on the standard. So that's when the Open Network Foundation was actually formed, the ONF, and where that standardization process was actually done, which is kind of interesting. So HP was way on board with that because we thought that was the right thing to do with them. So a lot of neat stuff has happened over the years now, and we're now to the point where HP actually has production code that we're shipping on our switches, on our routers, and several other types of devices that actually can do SDN. So we'll actually talk about some of the things we go through here. All right. Let's revert back because I want to make sure everybody really gets the concept of what was going on here. So I'll give you guys another analogy. So if we go back 25 years ago, and we go back to, and it's kind of funny, we were having a conversation actually with you about Zenu, and you said, DEC workstation. So if we go back to like the times of when DEC workstations are out, or anything from IBM or Hewlett Packard or Tandem or lots of companies that don't exist any longer, that when you went out and bought a large-scale computer, you got everything from that manufacturer. They gave you the hardware, they gave you the operating system, they gave you the API development kits. Oftentimes they gave you the applications. They absolutely gave you the support. Right? And you really didn't have too many choices as to what to do with it, right? You can maybe buy a third-party this or a third-party that, but you were pretty much stuck. If you picked DEC, you were DEC. If you picked HP, you were HP. If you picked IBM, you were IBM, right? You couldn't mix HP and DEC parts together. There just was no standardization. So back in the 90s, actually HP was one of the few companies that said, hey, there's this trend that's really starting to develop for people who want to actually decide what OS they want to run, right? So it was really all around running things on Intel processors. So they said, why don't we come up with the idea of actually having an industry standard server, right? And we're going to build out a standard parts that maybe can be mixed and matched on the hardware side. We're going to have multiple operating systems that can be loaded on it. You can write your own apps. We're going to give people an open environment, right? And obviously, that's what happens, right? That's what we all run today, right? We have this open hardware environment. We have this open operating system environment. We have an open operating application environments, right? So there's been a ton of innovation that's gone out there in the marketplace. But if we go to networking, we haven't had that. Us manufacturers have done a really poor job for our customers, or you might say we did a really good job for ourselves, was that we gave you proprietary hardware with proprietary operating systems. And you could probably say in the network there are applications, because you could say OSPF is an application, spanning tree is an application, QoS is an application, right? Can you change out the implementation of OSPF on your Cisco switch or your HP router? Absolutely not. It's stuck, right? In fact, it's a single blob of code, the whole operating system with all of the applications. So when you buy a device, it has all those things on it, right? Now, some manufacturers, they might give you a license key code that you can turn on a certain feature set, but you can't load any code, and you certainly can't write your own code. So what we think is that the time is right for SDN because we see it as that way that you can actually make a decision. Maybe the bottom layer I pick from HP. Maybe the control layer I go with an open source code set, right? Maybe the top layer I buy applications from wherever it makes sense. Maybe I go to F5. Maybe I go to Infoblox. Maybe I go to Citrix. Maybe I go to HP, right? I buy an application that runs on my network, right? That whole same concept that we have today on the server side, bringing that to the networking side. And that's what I think is really exciting. So just to break it down just a little bit more. So if you look at this first block here, this is a piece of networking hardware, right? It could be a switch, could be a hardware, could be a router. That if you look at that typical device, like that typical device has got two parts that it does: a data plane and a control plane, right? And the data plane itself is typically the ASIC that's inside the box. And the ASIC essentially is a pattern matching machine. It's looking for certain bits that come in, it looks at it, they match something in a table, it sends those bits out, maybe in another port in the ASIC, right? And those bits being an Ethernet frame, right? It looks for the Ethernet frame, looks at certain bits of the Ethernet frame, looks for a match, a destination, and sends it out the door. Now, the table that has the list of instructions as to what to do, you know, if you match this, do this with it, or send it out this way, that typically gets filled from the control plane or from a standard CPU that's inside the box that runs the operating system, right? And that standard CPU that's running the operating system also has the applications. Topology applications like OSPF, the spanning tree, the BGP, other operations that maybe decide to filter traffic or do QoS operations, or maybe even look at other things inside the packet. Those all happen inside the CPU, but essentially it all gets boiled down to instructions that go in the ASIC that are very simplistic, that says, if you see this kind of packet, do this or that. And in a software-defined networking world, what we do is we take that control plane that does all those basic things and we move it out of the switch and we put it up in a centralized order device, right? And what's really interesting to think about that is that if you think about a standardized network, if you think about, let's say this network here on the campus here, there's probably hundreds of switches, right? And all of these switches do a lot of the same things, right? One of those things that all those switches do is they figure out the topology of the network. Well, in today's network today, every single switch on Marquette's network figures out the topology. Now, shouldn't every switch have the same topology? And I guess in a perfect world, they all should have the same topology. And in a properly operating network, they have to have the same topology, because if they don't, the network doesn't work. But the funny part is that they all figure it out themselves, right? And I'll ask everybody a good question, right? So if we were all going to decide today if we're going to go take a trip to Madison, we're going to go to Aaron's lab, how would we all get there? Well, I guess Aaron could draw us a map, right? Or we could he could give us the address and we could all figure it out all ourselves. Or maybe somebody would pull up Google Maps and say, here's the address, what's the best way to get there, right? And most likely it'd be that third answer, right? And we'd all most likely take the most optimized route that Google Maps gave us. We wouldn't each of us figure it out all on our own. But that's what networks do today. Each switch, each router figures out how to get somewhere all by itself. So I think it's kind of grossly inefficient to have lots of different devices doing the same function, right? That sometimes don't always end with the same answer. So that's one of the really neat, efficient things about OpenFlow, is that we can take standardized things that everybody does, and optimize it by doing it just once and giving the same answer to everybody. And that way we can actually make sure that we have consistency as we get through the network. Plus, it's an easier point that if we want to make a change to the network, we can just make it in one place in the network, right? We want to affect it. So, the way that you have to do, the way you're able to do this is that you have to have a standardized way of talking to the switch. And that standardized way of talking to the switch is through an API. And there's one standardized API that's out today called OpenFlow. And it's That API allows the controller to tell the network device what the stuff inside of its tables on how to route traffic, right? And so it can actually do that in a consistent way across lots of different devices. Okay, all right. So we talked about some of the definitions here. Talked about the fact that we still have network devices themselves. Software will replace those. We still have to have ASICs as well within the mix. You have to have this abstraction layer that actually talks the API up to a controller. In that case, it's OpenFlow, which helps us decouple the data plane to the control plane. If you want to think about it, that controller itself kind of becomes a networking operating system, a true networking operating system. And then we can layer on top of it those applications themselves. So OpenFlow has been around, like I mentioned, for quite a few number of years today. It's a standardized API, and the neat thing about it is that it gives me a set number of commands and a set number of ways that I can match traffic to be able to decide on what to do. Now, when I actually tell a switch about things that I like to do, how I want it to either forward traffic, or to drop traffic, or modify traffic, I fill up what's called a flow table inside the switch. And you can actually do that a couple different ways. You can actually do it proactive, meaning that I tell the switch beforehand, hey, here's some certain types of traffic flows that you're going to see, and if you see them, you've already got it preloaded inside of you to actually be able to do that, right? So you don't have to adapt or learn. I've already pre-told you what I want you to do. Or you can have ones that are reactive, meaning that traffic hits the switch, and the switch says, oh, I don't know what to do with that traffic. I don't have a flow entry that tells me what to do with that traffic. So I can go ask the controller, I can ask an application, and then it can reactively give me information back on what to do with that flow. And you can actually have the switches can actually have this both. And we'll give you guys some examples of how you might have proactive and reactive ones. But to give you a little bit more thought on how this might look, essentially what you have when you have OpenFlow is you have rules, actions, and stats. So the rules themselves, essentially, I want to match something that comes in that hits the switch and it's a certain packet. So I might look at rule might be based on switchboard. Maybe we might look at VLAN ID. We might look at MAC address on the source side or the destination side. Ethernet type, IP source, IP destination. So we can match one or many of those things, and we also could wildcard, right? And then what do we do with it, right? Do we forward it? Do we copy it, forward it on multiple ports, which would be maybe a broadcast or multicast? Do we drop the packet, right? Maybe we want something else to look at, so we can actually maybe encapsulate the packet and send it somewhere for something to look at it and make a decision on it for us. Or maybe we want to modify something that's inside of it, right? So we've got multiple different things we can do. And then one of the other things we can also do is the controller can actually ask for stats about traffic flowing through the switch itself, right? So on what flow table entries did I hit? Did I have any hits, or did I have any bytes or packets per second on it? And so here's some really good examples, right? So I could have match rules like, hey, if you see somebody on TCP port 80 from this MAC address, maybe forward it off to an intrusion detection system, right? Because I want to take a sniff at it, right? Or TCP port 1634. Hey, maybe it's some streaming that's going on here, right? Maybe we want to rate limit it, but forward it, right? Or, hey, if it doesn't match any other rules, just forward like normal, right? Those would be some really good examples of stuff that could be already in the switch. There has been different versions of OpenFlow that have come out, so they've been looking at different ways to modify OpenFlow so we can do different things. And we're now up to OpenFlow 1.3, which actually I'll show you here in a second. So some of the neat things that 1.3 added was support for quite a few number of things. But probably the coolest thing is its ability to actually have multiple tables inside switches. That could allow you to actually break up the network in different spots, or have different rules for different spots of the switch. Also added on IPv6 support and a number of other things. All right. So back to another analogy here as we go through the rest of this. So everybody I'm sure in this room, or most in this room, probably have this exact problem, right? You go into your living room and you want to go watch something, right? So you got to go grab a single remote to go turn on the TV, another remote to turn on the stereo system, another remote to turn on the cable TV box or the satellite TV box. Maybe there might be a DVR. Who knows what it might be? Now, this is all fine for guys like me. It's like no big deal. I just turn it all on, works it all fine. But as soon as I go on the road, inevitably the phone's going to ring, and it's going to be my wife or one of my children. They're going to go, the TV's not working, right? So then you're explaining to them, it's like, all right, grab that remote, this remote, that remote, push this button, that button, and eventually they say, it's not working. And you're just like, oh man, it's got to be an easier way, right? So you do a little bit of research, and you go, I can go buy one of these fancy remotes, right? And that fancy remote can control the devices, and it even can do macros, right? So I can say, watch TV, and it actually can turn on multiple things at once. Now, the reason I brought up this analogy is it's a little bit like software-defined networking, right? So all of those remotes all use IR to send commands to a device. And that command is pretty simple. It's a set of binary bleeps. And you get 3 binary bleeps that says turn on, you get 4 that means turn off, or whatever it might be. And it's pretty simplistic, right? And it's a lot like software-defined networking, which is, the devices themselves can be fairly generic, the TVs, the VCRs, and things like that. The IR command set that I've given to them is a lot like the OpenFlow, right? And the macro stuff, like if I wanted to do multiple actions all at once, is a lot like applications, right? So what that allows me now to do is to actually, now, if I take the analogy of my living room, it now means that, well, I don't have to make sure that I bought everything saying Samsung on it, so that I can pick up one remote that controls all my Samsung stuff or all my Sony stuff. It means that I can go, who's the cheapest price on the TV? Oh, Seiko. Who's got the cheapest price on the stereo system? Harman Kardon, right? And I can buy one remote that allows me to glue it all together and actually make it feel like, I've got something, quite sophisticated, right? And so I've made it so that I can pick and choose and make the right decisions. And SDN has the capability of doing exactly that. I might buy the right switch for this part of my network, the right router for that part of the network, and they could all run OpenFlow, and I can have applications on top of that control them. It means I can do the right things in the right places. I might use a really inexpensive switch in this place, a really expensive router in that place. Whatever makes sense based on my performance. Okay, so a little bit of HP commercial here. So we're proud to say we're actually one of the first companies out there that has come out with products that actually that we have the whole stack. So my slide here just says 40. We're actually up in the 50 plus switches that actually have OpenFlow enabled on them today, which means that they can be controlled by any OpenFlow controller. It could be one coming from HP, it could be an open source one, it could be from a third-party manufacturer, and will allow them to actually get their forwarding information, their control plane information from that centralized spot. We also have our own controller called the SDN controller. And this is a software application that can actually run on a virtual machine or on a physical piece of hardware that can send via OpenFlow commands down to devices. It can also run applications on it or talk to applications that are outside the controller. We're one of the first companies also that has applications that are also coming out right now that allow you to actually do that. And then if you're in an environment where you might have multiple controllers, which we do see happening, possibly in different parts of the network, you might have a controller that controls just the campus. You might have a controller that just controls the data center. You might have a controller just the WAN, maybe for the wireless network. That you might want to provide network management and orchestration between all those different controllers. And we actually have network management that allows us to actually manage multiple controllers and deliver policies in the same way to all those controllers that are out there. Alright, so let me talk through a few applications so you guys can start to get some of the ideas. I'm going to use some HP ones here. I'm going to throw out some other third-party ones here as well to talk through it. So if you were to launch a cloud data center, like an Amazon or an HP Helion, right, or any of the other number ones that are out there that have different brand names, one of the whole ideas around cloud is speed and agility, right? I want to be able to move applications out of my data center into another data center very easy, very quickly, right? And I might need to do it. I mean, I might not be planned for it. And that's actually probably one of the reasons why Amazon Web Services is so popular, is because if I also doesn't have a project and I need to compute, all I need is a credit card. I go to Amazon Web Services. I can actually buy compute right now for any number of machines, any number of storage I want, and I can rent it by the second, right? And so I very quickly can go and increase the size of my data center, either because I watch an app and I'm like crazy, I open up a very popular store and everyone wants to get there, or whatever it might be, and all of a sudden I'm popular, I can actually find more compute to do it. Well, one of the problems is that if you're an Amazon or an HP or any other number of cloud providers out there, then you don't want to be hiring hundreds, if not thousands, of people to like staff telephones and say, "Hi, would you like a compute cluster?" You actually want to just go to a website and say, "I need 32 cores, I need 192 gig of RAM, and I need 10 terabytes of storage. Oh, and I need a gigabyte of memory, right, for my application." You just want to go click on a website, and on the back end, you want the infrastructure provision itself. So one of the apps that we wrote internally for HP Helion, that's HP's public cloud, is this app that allows us very quickly that when you go provision compute resources in our cloud for your use, that you can also provision the network access to those compute resources, right? So we can actually provide routing services, we provide firewalling services, you can set up VLANs, you can say this server can talk to this server, but it can't talk to the internet, all for a web-based interface. And that's done today using software-defined networking. So the app itself, when you go to provision, it essentially sends those commands via SDN, via OpenFlow, out to the switches, and allows you to actually program the switches from an easy-to-use web interface. Okay, so one of the other interesting apps, and you see Intel Verizon up there on the logo piece there, but I've seen this also without the open source community. Some of the universities are doing research. All of us we kind of have the same exact problem, which is I might have multiple data centers, right, between multiple campuses. And I have applications that might be sitting in data center A and being utilized very little, and then next thing you know, a lot of people want to use those applications. We start to spawn off more applications into potentially other data centers, right? So for people to get access to those apps of those other data centers, I'd be able to need to provision the network very quickly to say, hey, I need additional bandwidth going to these data centers for these applications. And so the ability to tie in those applications to tell the network that they're in different spots, either they need more bandwidth, is one of the neat things you can do with SDN. Another neat thing you can do with SDN, not mentioned on this, but one that I definitely seen research papers about, is the ability to have data centers that for applications that move between data centers that follow the cheapest place to operate, right? And usually that cheapest place to operate is based upon cost of power, right? So you might actually have an application that sits there and looks at the cost of power globally at all your data centers, right? And it indicates that right now, the cheapest place you can get power is Malaysia, right? So, a very optimized, very orchestrated infrastructure could actually say, hey, let's start provisioning VMs for this application in the Malaysia data center, right? And as soon as the provisions are up and operational, go off via SDN and provision the network to move that traffic path to go to the data center in Malaysia, getting you the best cost per kilowatt hour for those compute resources at that data center, and then continuing to monitor it, saying, hey, if Malaysia prices go up because all of a sudden it's 100 degrees in Malaysia, you might decide to move those resources off to your data center that's in Sweden, right? And then continue that thing all automated all the time, right? You would never have a group of network engineers that were sitting there reprogramming the network at all, right? It doesn't make any sense. That kind of thing might happen day in, day out. So an application that HP wrote is one more specific to a specific application. So a thing that happens quite often at a lot of places is that we've deployed voice over IP, right? It might be a hard phone like that one, or it might be a software application like Microsoft Link, right? And so when you do voice or you do video on a network, you're tearing up and you're tearing down conversations all the time. But when you tear them up and tear them down, you need them to be ultra good quality, right? You need them to be low latency, and you don't want to lose patterns. And today on our networks, we generally use something called quality service or QoS, which essentially, the way I like to think of it, is a technology where we observe things and we're able to react to them. And what I mean by that is the fact that if I have some voice traffic and I want to get it from myself over to Steve, what I'll do is I'll overgeneralize. I'll put it in a red envelope, right? And I'll hand it off to the network switch. And I assume that the network switch knows that a red envelope is really important. And he's going to pass it on to the next network switch. But we also assume things that a red envelope is really important. And it eventually gets to Steve, and he gets it in time and it works okay. But if along the way I throw a red envelope and some switch along the way doesn't think a red envelope's important, it might not treat it the way we want it to, and we don't get good voice quality, right? And so there's kind of a network provisioning issue with that, is that I need to do it consistently. Because if one switch thinks that red is important and another switch thinks green is important, it fails, right? We really oversimplified it. But that's pretty much the way QoS works today. And of course, I could fake it. I could take non-important stuff and put it in a red envelope and send it along its way. And other people are getting starved resources because I broke the system. So what this application does very specifically for Microsoft Link is it allows the Microsoft Link server to tell the network that Jeff and Steve are going to talk to each other. And so now the network specifically sets up a path for us to talk that's the right latency and has the right packet loss characteristics that we want to have that conversation. And then when he and I are done talking, the network doesn't just notice that we stopped talking. It's told, because when I hit the hang up button, that was I clicked the button on my soft phone. The Microsoft Link server saw that, and it actually told the network we're done talking. And it shut down the conversation. So that's actually a real app that is actually shipping today. All right. So another application that we thought was very interesting was the ability to take network devices and give them new applications that they never had before, right? So network switch today pretty much switches. Some of them route, but for the most part, all of them switch. Does a few other extra things. But what if I wanted to make it into an intrusion detection device? What if I wanted to make it into a firewall? What if I wanted to make it into a load balancer? When you really get down to it, any kind of network device really has two functions, right? Control plane function, forwarding plane function, right? So the forwarding plane function is exactly the same. look for a packet that matches a certain thing and do a certain operation to it, right? You just need a smart control plane to tell the data plane what to do. So whether it be a load balancer, an IPS, firewall, it's for the most part kind of at the basic level doing the exact same thing. So we got this really great idea at HP of taking one function of an intrusion prevention device and being able to tell it what you'd probably consider a pretty dumb layer 2 switch how to do it. And so what we did was we came up with the whole idea that if we wanted to make sure that end user devices did not go to bad places on the internet. And these bad places, I would say, would be places that host malware, that might be known to essentially be a fake shopping site. It might be places where you might get with a threat locker, essentially where you'll get a piece of malware that will actually lock down your machine and you'll have to actually pay it back using a credit card. Whatever it might be, it's not a place on the internet that you might want to go to, and it's very easily stopped, right? And it's very easily, we know about most of those places. In fact, actually, HP keeps a database with about 700,000 entries that say these are places we just know you don't want to go there on the internet because you're going to get into a security issue. So, pretty easy way we could attack that. If we attacked it the old way, we'd force you to go through a network device that actually looked at your DNS request and said, oh, hey, that's matched the database, let's drop that packet. But in a large-scale network, I don't want to throttle everything through one device. Well, no problem. I can actually easily make that happen. I can put a flow table entry into all my Ethernet switches that says, if you see port 53, DNS, send that packet up to this application that can go inspect the DNS request. If the DNS request matches an IP address that's in our bad database, we can actually tell the Ethernet switch down below that's bad traffic, drop it. So we've actually taken generally a dumb layer 2 switch and we made it slightly smarter, being able to do a simple IPS function. As I mentioned before, we're actually shipping a SDN controller that runs OpenFlow. We call it our Virtual Application Network Controller, VAN. Runs OpenFlow 1.0 and 1.3. But there are other controllers out there. There's a lot of open source controllers that are out there. As long as they all run OpenFlow, they can at least minimally talk to our network devices or any other network devices that run OpenFlow. And that's kind of the beauty of OpenFlow, is that. But the key comes in whether or not you can actually run the applications you want to. Obviously, some controllers are out there more developed for doing research, and Aaron is going to talk to us a little bit about that. But other ones will actually be more built around commercial applications that will actually pop out there. Now, those commercial applications that pop out there, one of the things they're going to need is an API to talk to the controller. And that API, we call that kind of the northbound API. And that's in reverse to what you probably would consider the controller talking to the switches. Guess what? That's the southbound API. But that northbound API allows applications to be able to easily ask things about the network without having to know network level stuff. Some of those applications can actually sit on top of the controller or potentially can be out there of the controller, right? And so things like Microsoft Link, the app that I talked about, or the Network Protector app, or some of the other apps I talked about as ideas, those would use that API to talk to. In fact, actually, let me give you guys another example of an app that could use the API that somebody could write. So, really good example. So, we walked in here an hour and a half ago to get ready for this. And when we got here, the doors were locked, right? But one of the neat things, that could have happened was that there could have been this amount of this data that could have been shared between the building and the network and back and forth again because we had one key person here, Steve Goodwin. So if the building had known that Steve was in the building, they could have actually said, hey, Steve has got this room reserved at 12 o'clock. I noticed that Steve's in the building. I could actually unlock the doors, right? Well, how could that happen, right? We might say Bluetooth, NFC, facial recognition, right? But no, I got something really simple. It's called Wi-Fi, right? So Steve has got his phone that's already authenticated to the network, walks in the building. We know Steve's in the building, or at least Steve's phone's in the building. Hopefully they didn't lose it. So it's a proxy for Steve being in the building. So if the building had a way, according to the network, to see if Steve was in that building, it could actually have some logic that said, hey, go ahead and unlock the door, or turn on the lights, or turn the temperature, right? Or the reverse. Hey, maybe I'm trying to watch my energy usage in this building. I could actually monitor the Wi-Fi and say, oh, interesting. No one's in the building. I guess I can turn down the heat. Right? I can save money because I don't see anybody connected to the network. And nowadays, people connected to the network, it's pretty much 100%. Right? You're not going to see people not connected to the network. All right. I mentioned that some of the applications can actually run inside the controller. There actually is a internal API that allows them to do that. There's only a few applications you would normally run inside the controller, and that would be kind of like network-oriented applications that look at the API or do QoS functions like that. The vast majority of most applications would actually run outside the controller because they want to talk to other applications or you want them to be scalable. I talked about the southbound API. The southbound API choice today has been OpenFlow that we've talked about several times today. The controller is the one that talks to the southbound API in those devices. There could in the future be other southbound APIs, but the whole reason that OpenFlow was developed is a great way to actually disassociate that control plane from the data plane. It was designed just for that. I mentioned previously before, you actually still can have the concept of management. We'll actually show you a little bit of demo of that in a second, just so you're aware that is possible. And as I mentioned, management can play a role if you actually have multiple controllers out there, or if you want to actually put a graphical analysis on top of what you're actually doing. Now, one other app that could come into play is when you actually want to tie the network into other resources out there, whether they be storage or whether they be compute. And so one of the most popular ways that people today control the hardware in their data centers is using VMware, right? That allows us to carve up hardware for hardware resources in different ways. So what we did was we came up with the concept of actually being able to interact with VMware so that we can actually be told about new virtual server instances being created and be able to actually automatically create network instances that match up to those virtual machines that are being attached to the network. And as they get attached, more virtual machines get attached, we can actually attach their network profile, and if they get spun down, we can actually take away their network profiles. And if you're actually using VMware to tie together through their NSX, their virtual machines, we can actually provide APIs that allow their virtual tunnels to actually tell the virtual network about, or the network underlying what to do.
So,
yes?
Just as a question, on the VMware NSX side, I've kind of not implemented yet, but I've kind of seen demo implementations where they're exchanging routes like with OSPF or something like that on the hypervisor side so that you don't have to reconfigure the switch.
Right.
So on the HP side, you're saying that the networks can be provisioned on the VMware side, and then you can create those networks dynamically, for example, off of your core and then route those?
Correct, exactly. So let me give you a couple examples of where that makes a lot of importance. So even though a lot of people are virtualized today, not all applications get virtualized. Sometimes we leave a few of them to actually run on bare metal servers. Usually you're going to see these in big data environments. You might see some SQL servers and things like that when we run on top of bare metal. So that means that you can't do a tunnel through NSX from a virtual machine to a physical machine, right? So that's an area where you actually need a drop-off point where you can actually end the NSX tunnel. So we actually have the ability in our switches to actually terminate those tunnels from NSX and then provide that linkage between the two. So that's area one. Area number two is that while in theory it seems really interesting that I can actually create a tunnel, a network tunnel between two virtual machines, and I don't have to care about the underlay network, the physical network that's underneath. I'm just going to expect that it all works and that this guy has got 10 gig of throughput between these two places and 40 gig of throughput between these two places. But what happens if the underlay network, if a switch goes down or some ports aren't active or a cable's broken, right? So underneath here, there's a part of the network that's not as good as I expected it to be. And you have this operation up here, this tunnel that's going on, that just says, well, I just assume that the network's going to carry this, right? And maybe there's not as much bandwidth between those two places as possible. So one of the things that we can do with our integration is we can actually tell NSX about the status of the network underneath it. We can tell it how much bandwidth is available between point A and point B so that it doesn't assume that it can actually get between those two places. Because sometimes hardware does fail, right? Because of power, because of cabling, whatever it might be. Does that make sense?
It does. Do you see that tunneling technology with NSX being relevant in multi-site data centers or DR for things like that?
Sure.
For just that layer 2 elasticity? Or?
Absolutely. And then that communication between the underlay and the overlay network becomes even more important. Because as we well know, once you leave the data center, you have more chance of failing, right? Because also now I got to fend into the backhoe, right? Rather than a network tech that just tripped over a cable.
Sure.
Yeah, that's a good question. So, one of the things that we think is really super important is that there has to be a strong ecosystem. That's why we get really excited about SDN, is the fact that it's based on open standards. It's based upon the whole idea of having the ability to have different applications, different controllers, maybe different network elements. And we think that having a strong ecosystem is going to drive it even stronger so we can actually build better networks today. So one of the few things that we're doing, and you're going to see this very strongly, is the fact that we actually have an open software development so people can write and work on it. I think that's super important. One of the other things we're going to do is bring out an application store so that if you want to look for applications, whether they be ones that are free, ones that are ones from HP, or ones that are from a third party, you can find a place that they're validated and you can try them out in an easy way before you actually implement them on your network. And you'll see that coming out from us here very shortly. And then lots of different people out there that will see, they'll come out with applications. We actually have several companies that are actually coming out. Companies like Blue Cat, would be an example, will be one company that's coming out with a DNS application. And there's several other companies that will be coming out with those applications here pretty shortly. So, with that, I'd like to ask Mr. David Spears to come up here and actually show you a real working SDN.